Tech giants are pouring billions into massive data centers, locked in a high-speed race to build the ultimate artificial intelligence. Online, the debate is endless. Every week, a new leaderboard claims Model A has finally overtaken Model B in raw processing power and reasoning capabilities. Yet, when everyday users log in to try these top-tier systems, the results often fall flat. They ask a question and get back a generic wall of text, or worse, hallucinated answers that sound plausible but are entirely fake. This friction happens because we treat advanced neural networks exactly like traditional search engines. We type a few keywords into a box and expect a perfectly packaged answer to appear on the screen. But large language models, or LLMs, AI systems trained to recognize and generate human language, operate more like students in a classroom. In any school, different students have different strengths, but none of them perform well without a good teacher giving them clear instructions. Staring at technical leaderboards distracts us from our own operational failures. The breakdown usually isn't in the code, it is in how we guide the system. This diagram outlines AI performance. The central node is our model. Test variable A, a generic prompt. With zero context, it yields a bland, mediocre output. Reset for variable B, supply specific context and strict constraints. The model now produces a highly nuanced, expert-level response. The architectural quality of your output is directly correlated to the structural integrity of your initial prompt. To understand why guidance dictates the output, we have to look at the internal mechanics of these tools. Large language models are essentially probability engines. A probability engine is a mathematical system that calculates the statistical likelihood of what word or concept should logically come next in a sequence. With a generic prompt, the probability engine is unmoored. Data points explode outward in chaotic directions, causing high variance. Apply specific constraints, and you force those probabilities to narrow. The system stops guessing, converging on a single, precise trajectory toward your target. This mathematical narrowing process is the literal equivalent of good teaching in our classroom metaphor. You are providing the exact parameters the system needs to succeed. Your instructional clarity has a direct causal link to the mathematical probability of the AI generating a successful output. Stepping away from the abstract math, this applies directly to your daily workflow and how you build your projects. It invites a moment of reflection. Have you seen the same model perform completely differently based on how you interact with it? Getting consistent value requires abandoning the passive, query-based habits we developed over decades of relying on standard internet search engines. The required operational protocol means treating artificial intelligence like a highly capable employee. It demands active management, clear boundaries, and continuous instruction to stay on task. Evaluating which AI model is technically the smartest is functionally irrelevant for the modern professional. The raw computing power is already there. In a world where raw intelligence is becoming a commodity, your value is determined by your ability to lead these systems rather than just access them.